So this is actually an introduction not only to chapter 23 in geometric optics, but also the first unit of what we'll talk about in 1070, which is, broadly speaking, optics. Um, so you could think about this as a maybe one of the more fundamental questions about the human experience, like what is light and vision? So you open your eyes, what are these visions that you see in front of you actually made out of? Like what's going on? And there's no shortage of really interesting ideas, very creative, that date back as long as people have been keeping records. So I think one group of ancient Greek philosophers thought that tendrils actually reached out of your eyeballs, kind of felt up the thing that you were pointing them at, and then reported back to you. But we'll actually pick up with these two guys because they spoke the language of math, and this is the way that we talk about things in physics. So this is Isaac Newton on the left, and his contemporary, you can tell from their amazing outfits and wigs, on the right, whose, I guess, anglicized name would be Christian Huygens. I'll try to pronounce it once, like a proper Dutch person might. And they were contemporaries, and they both had a competing theory of light that we would recognize as kind of like a modern one. It actually depended on, things that we would recognize as physical ideas. And Newton actually thought that light was made out of particles. So what happens when there's a candle burning, for instance, is the candle is literally ejecting particles towards, your eye, or they bounce off the wall, which is why the wall is lit, and then they make it into your eye. And what's actually happening is the flux of particles hitting your eyeball and putting pressure on it causes you to see stuff. Maybe the harder the particle, the brighter the color. And Newton went so far as to test this theory by doing things like taking stop the video if you're squeamish, but taking a blunt metal pin and putting it in between his eyeball and the socket. And sure enough, he saw a lot of like weird distorted shapes and colors. So therefore, it must have been the pressure. Newton was nothing if not dedicated to science, I guess. Conversely, this guy, Christian Huygens, thought that light was a wave. So it was a wave phenomenon like a water wave or a sound wave. And he had a lot less observational evidence, but it turns out that he's actually right. So what made Newton's argument, and the people who came before him, it's not just Newton, so compelling is really point one, is that light travels in vacuum. So all of the other waves that we know actually travel through a medium. Water waves travel through water, sound waves travel through air, for instance, and light seems to travel through nothing. So the sun emits light, that light travels for 149 million kilometers, bounces off the moon, and then makes it down through another stretch of vacuum and then into our eye. That's a lot of nothing to travel through. And water or sound couldn't do that. So secondly, light travels in straight lines. So maybe like a particle that was thrown might. You've never really seen, something like a laser travels in straight lines, and you've never really seen something like a water laser. So get in even a still lake and splash your hand all you want. You're never going to make this perfectly collimated beam of water like a laser might, not like Newton had access to lasers. So light reflects and light travels through different boundaries, so from water to air, for instance. But reflection and transmission don't really sway the balance for a wave or particle because both particles and waves do this. So if I threw a ball into water and it was really heavy, it would keep going through the water. Likewise, if I threw a ball against the side of a pool, both that and a water wave would bounce off the side. So it's really these two things, which we'll talk a lot about in the chapters actually following this, which would be the smoking gun, that light was actually a wave phenomena. Waves and only waves diffract and interfere. So diffraction is when you have a wave and it spreads out as it goes either through some gap or around an obstacle. So here's an actual picture of water wave diffraction. You can see the crests of the water waves and the troughs spreading out in this kind of circular pattern. Here's a cartoonified version where what this dark line indicates is where the peak of the wave might be. So for instance, this would be a crest and this would be a crest, and it's being passed through this narrow gap and then they spread out. So in fact, you actually see this phenomenon in speaker design. So bass speakers are really big and treble speakers are really small. It's not because you need a big speaker to make low notes. Like if you have, earbuds can make perfectly low notes. They don't sound particularly good, but you can make them. What's really going on is it's the treble speakers that need to be small because you want the sound to diffract. So you want the wave to diffract and fill the room. What you don't want is like a sound laser where you can only hear the speaker if you're standing right in front of it. You actually want this to occur. So Newton actually knew a bit about diffraction and light. The edges of shadows are kind of fuzzy. And what Newton argued was that it was actually the particles pushing each other aside. So fine, Newton, you're a pretty persuasive guy. What we really need to do then, and what would really prove Huygens right, is to see interference. So what interference is an absolutely waves-only phenomenon, where if I have two waves that show up at the same place in the same time, they obey what's kind of pretentiously and grandiosely called the principle of superposition, where I take the individual waves and I add them up. So here, for instance, in this picture, there's a possibly deranged man who's splashing two balls on a stick into a still pool of water. So there's wave disturbance number 1 here and wave disturbance number 2 over here behind where his head is. And what you can see is constructive and destructive interference where the two waves meet elsewhere in the lake. So constructive interference happens where crest meets crest or trough meets trough. So if I have two troughs meeting, they add up and they're extra low. Whereas if I have two crests meeting, high point and high point of the wave, they're extra high. So this would be a locus of constructive interference all along this line. So you see the high points are extra high, the low points are extra low, compared to somewhere out here, low point extra low, high point extra high, constructive. Conversely, if you have trough meet crest, low point meet high point, or crest meets trough, high point meets low point, the high and the low will add up and cancel. So that's destructive interference. And that would be these loci where the crests and the troughs meet, and so you get total cancellation. So this in particular really is definitely not a particle phenomenon. So when two particles show up at the same place in the same time, they bounce off of each other. So you've never seen two tennis balls hit each other in midair and all of a sudden they both vanish because one of the tennis balls was upside down. So absolutely not a particle phenomenon. And this was observed in 1800. So we'll spend a lot of time on the theory of this later in the quarter. At least maybe hopefully virtually you'll see a lab on this and some demos. But in 1800, somebody, English or Scottish guy, carefully took a razor blade and cut up some playing cards and was able to actually see this phenomenon with light. And in a second you'll realize why that's so impressive. But even still, people really didn't believe that light was a wave, and Hawkins' theory wasn't universally accepted. It really took until 1864 and proof that not only was it a wave, but it was a particular type of wave, an electromagnetic wave. So this is what you learned in 1060. It might not be exactly the way that you remember seeing it, because this is kind of calculus language. But these last two lines of what are collectively called Maxwell's laws are two things that you have seen before. So in this GIF, there's a guy plunging a magnet into a coil of wire. And you can see the needle on this meter dip because what the changing magnetic field is doing is creating an electric field, which thereby pushes some current through this ammeter. So changing magnetic field makes an electric field. So you see the opposite of that if you have a changing electric field. So if you have an inductor, so one of these coils of wire, and you're putting current through it, and let's say that instead of using a changing magnetic field to make a current, forget about the magnet, I'm just putting some current through that coil of wire, and then I unplug it, it doesn't like that change in electric field, and it will try to make a magnetic field that brings the current back. So these two things you either hopefully believe exist, or you've probably seen in practice. So the changing magnetic field making an electric field, that's actually how power is generated. So you have a turbine in like a hydroelectric plant, it's spinning, the changing magnetic field makes an electric field. And then if you've ever unplugged a toaster while it was still trying to toast, what you've seen is a changing electric field make a magnetic field. So that spark that comes from the outlet when you pull a high use appliance out of the outlet while it was still going is actually this, the lower phenomena. So what Maxwell realized and proved mathematically is, wait a minute, I have changing B making E, but then I have changing E making B, but then I have changing B making E, and E makes B, B makes E, E makes B, B makes E, and so on and so forth. And what you get is an electromagnetic wave. And this explains why it's such a funny wave and travels through vacuum, unlike most other waves that we know about, is that really what's happening is the electric field is using the magnetic field as a medium, and the magnetic field is using the electric field as a medium. So it's kind of bootstrapping its way through space and can travel through absolutely nothing. So at this point, people definitely believed that light was an electromagnetic wave. Newton, you're wrong. So why did it take so long? Again, this is what is light and vision is maybe one of the first questions you might ask if you were doing physics. And, you figured out mechanics in the 17th century. E&M was figured out largely in the 18th and 19th centuries. By this time, thermodynamics had been figured out too. So the other way of saying it is, what happens when you open your eyes really was only resolved 40 years before we got knee-deep in quantum mechanics. And the answer for that came from Maxwell as well, is that light has a teeny, teeny, tiny wavelength and a really big speed. So the wavelength of light, if you take 1 millimeter, which is a little bit thicker than a fingernail, and take 1 millimeter, cut that 1 millimeter into 1,000 pieces, take one of those pieces, cut that into 10 pieces, that's about the wavelength of light. So teeny tiny. And by way of syllabus, the thing that kind of unifies 1070, it seems like a grab bag at times, but really the thing that unifies 1070 is the fact that all of this stuff is actually pretty modern. So thermo is pretty recent, light, the final description of light is pretty recent, and quantum mechanics obviously is pretty recent, as well as nuclear physics. So basically modern grab bag. So turns out that visible light is not the only electromagnetic wave, and that all of the stuff on the electromagnetic spectrum is successfully described by the stuff that we'll talk about in this class. So radio waves are just a really long wavelength form of light. So the phone that you use to communicate is actually a battery-powered microwave that you hold up to your brain. That's this type of light. And then at the other end, there are X-rays and gamma rays, which are very, very short wavelength light, even shorter than visible light. So this is about 21 orders of magnitude, at least on this chart. So it's an astonishing amount of phenomena that can be described by both geometric and wave optics. Okay, so why even bring up Newton at all? So that's really what chapter 23 is about. We didn't do it just to point out what a weirdo he was, poking himself in the eye for science. And, it feels good to dunk on Newton, but really the point is that it took so long to figure out that light was actually a wave because the description of it as a ray or a particle is really successful. So what we'll call geometric optics, which really is modeling light as arrows kind of shot through space, and they can move through vacuum in straight lines. So geometric optics is really good at describing, successfully describing and predicting a lot of stuff. So reflection, which is where we'll start, refraction, so that's when light, for instance, goes from one medium to another. And then optical instruments, starting with lenses and mirrors, both flat lenses and mirrors and curved ones, and then optical instruments that you can make out of them. So telescopes, microscopes, cameras, all can be described by geometric optics only. And the start of geometric optics, at least the first treatise on it, is I think from the 9th century, so an Arabic text. So pretty old and pretty successful.